Hello, everyone. Dr. White back again with another screencast in our section 5.1 on estimators and the variability of them. Last time we defined some basic concepts like parameters, which are numbers associated with the population, statistics, which are numbers you compute from a random sample that you drew from that population, and you use statistics to estimate parameters. For example, you might use a sample mean to estimate the mean of a population, or you might use a sample proportion to estimate the proportion in a population that has some characteristic. And we promised to focus on one proportion situation in this section. Here we go. So let's give ourselves a hypothetical population so that we can kind of pretend to be God, as it were, who's able to know everything and knows everything about this population. And then we can watch what we model as statisticians sampling from that population and sort of watch how it is for them as they compute estimators and make their own guesses about what's going on in the population. So this imaginary population is a data set in the TigerStats package called ImagePop, and we need to learn about it. So I'm going to copy the help and view commands on ImagePop, head over to our studio, and in the console here, paste in. Okay, so the help tells me that this is just an imaginary population. It's not real data taken from anywhere. Every row here in the view is an imaginary person in this population, and we've recorded various variables on each person, their sex, male or female, whether or not they are math majors, lots of no's there, oh, there's a yes, their income in dollars, I guess, in a year. Kapun is whether or not the person favors or opposes capital punishment. Height in inches, the height they would ideally like to be, the difference between those two heights, and K-Kardash-Temp. So this is your feelings about the celebrity Kim Kardashian on a scale from, I think it was going to be like 0 to 100, where let's check the help here. I might have to move my face. Can I move my face? Lately, I'm having trouble moving my face. Yeah, 0 to 100 scale. And 0 is like absolutely hater, and 100 is lover as much as you ever possibly could. 50 would be like neutral. Okay, so we've learned about this data set. Let's head back to the slides and see what we'd like to do with it. So we've learned about these variables. Let's give ourselves a research question involving a population proportion. What proportion P of people in ImagePop favor capital punishment? Okay. So the parameter of interest here is P, the proportion of all individuals in that population who favor capital punishment. And it's something that we're going to be able to know because we have that whole population in front of us. But we're going to imagine statisticians who don't know, who are not able to have the whole population in front of them, and all they can do is take random samples from that population. And they will compute the sample proportion, this p hat number. They will compute the number in their sample who favor capital punishment, and they'll divide by their sample size. So symbolically, X here is how many in the sample favor capital punishment, and N is the sample size. And that's their sample proportion. So we can watch these statisticians do this with a function that comes from the TigerStats package called prop sampler. All you have to do is tell it what categorical variable you want to work with. It needs to be one that has just two answers, like Kapun, is favor or oppose. And you need to say what data set that variable lives in. So you can try this function on anything, but we'll try it on a MagPop. So I'm going to copy, head back to our studio, and paste in. And I'm about to run it. I don't want my face to get in the way, so bye-bye face. And I think I might also just make the plotting window bigger here before I start out. And get back over to the console and press enter. Alrighty. So what we have to start off is just a little bar graph that shows us what's going on in that population. The height of each bar is the proportion of people who have the given attitude. The height for the favor bar, favoring capital punishment, is actually 0.298 exactly. So 29.8% of the population favors capital punishment. And the rest oppose capital punishment. Now, there is a little cog, and we can push it, and we get a little manipulator widget. We can have statisticians, we can pretend to have statisticians take random samples from this MagPop. Look at a MagPop over here. It says it's got 10,000 rows. So there's 10,000 people in the population. And right now it's set to take a random sample of size 10. So why don't we go ahead and just push on, let's just click on that little button that's set right now at the 10 and see what happens. Look in the console. So we got 5 favoring and 5 opposing in our sample of size 10. And so if you're interested in the proportion of people who favor capital punishment, then that would be the 5 who do divided by the 10 in your sample. That is 0.5, and that's what they say p hat is. And they also go ahead and tell you the population proportion. It was 0.298. So this imaginary statistician stuck with a sample of only size 10 was fairly far off. You know, her estimate of p would be 50%, when really it's near 29.8%. She's pretty far off. Let's have a statistician do it again, sample size 10. Okay, your results are going to vary when you're trying this along with me because you're having R do random looking stuff. For me, 2 favored out of 10, so the p hat was 0.2. By now, the plotting window shows a density plot of the p hats that we've got so far. We've got 2 p hats. One of them was at 0.5, and you can see that little tick mark that I'm waving my arrow around. And the other was at the 0.2. That was the second one. And the very last one that you've done will always show with a blue dot, okay? The others will just show with tick marks. That vertical line here is at 0.298. That's where the population proportion P actually is. Okay, so let's keep on pushing the little button to get more imaginary samples of size 10. So we watch another statistician go. That one got a 0.5. Another one got a 0.2. Another one got a 0.4. Another one got a 0.5. Another one got a 0.1. Wow, like, you know, way off. Another one got a 0.3, almost right on. Another one got 0.2. And you can just sort of keep doing this. And since it's sample size 10, the only possible p hats are 0 or 0.1 or 0.2 or 0.3 or 0.4 or 0.5 and so on, all the way up to a 1. And so the density, the rug on the density curve doesn't look very interesting because these tick marks are, you know, over plotting each other. But you can see that the population is fixed. I mean, the population parameter, P, is 0.298. That's fixed. It depends on the population, which stays the same. It's the p hat, the sample proportion, that's the random variable, the thing that, changes from one sample to another. It's trying to estimate the p, but it's going to be off by some amount, sometimes not by much, sometimes by a lot. Okay, let's change things up. Why don't we try like a bigger sample? How about we move it up to sample size, I don't know. The slides say 110. I feel rebellious. I'll go to sample size 100. Okay. So once we moved it up, we got our first sample of size 100. 31 were in favor, 69 opposed. So our p hat was 0.31, pretty close to p actually. Now this plot over here still pertains back to the old sample size 10. So we don't look at it at the moment. But let's take another sample of size 100 by clicking on the little button. And now it switches over to trying to make a density plot of the p hats that it's got so far for this sample of size 100. Let's see. This second p hat was a 0.33 because we had 33 out of 100 favoring. Let's keep on taking some p hats one at a time. New samples of size 100 from this population every time that I click. And this one you want to do for a little while. You want to see how those p hats are coming together to make a little distribution of the sample proportions. You get to see what kind of p hats are more likely and what are less likely based on the height of that density plot that's being made. One thing I notice at the larger sample size is that the p hats tend to be a lot closer to the p than they were back at sample size 10. Sometimes they're lower, and sometimes they're higher than the real p, but they're around p, and they tend to be closer to p than the p hat for sample size 10. So the variability in this estimator p hat seems to be smaller at larger sample sizes. Another thing that you might notice is that the density plot itself looks somewhat bell-shaped, and that is no accident, and we'll be talking about that soon. Okay, I feel like I've played around enough. I'll head back to the slides. So let's review the lessons you learned by playing around with that little app. Your sample proportion p hat isn't necessarily going to ever be equal to the population proportion p, but it is going to be around the population proportion, give or take some for chance variation in the sampling process. Okay? And the other thing that we noticed is when the sample size was bigger, the give or take was smaller. And we also noticed that p hat definitely has a sampling distribution. Once you've got enough of those p hats together, their density curves seem to, stabilize to have some particular shape. And at larger sample size, it looked roughly bell-shaped, very significant. And of course, the distribution appeared to center around that vertical line over the p. Whether the sampling size was large or small, it did seem to center around p. So I'm very interested in this give or take figure for the estimator p hat. That's what we call a standard error, and let's study these. So any point estimate, sample mean, sample proportion, sample median, all these other types of estimators that try to estimate parameters in a population, they are all going to have what we call a standard error, SE for short. Standard error for point estimate is a measure of how much it's liable to differ from the parameter. And so the way that you'll think about it once you know how to get a standard error for an estimator, you'll say to yourself, the parameter that you don't know is about equal to the point estimate that you got in your sample, give or take a standard error or so, and you'll be able to compute that standard error. So it's great to work with your estimator to give an idea where that parameter might be. So what you need is a way to get standard error for your estimators, and mathematicians come along and they help you out as much as they can. Turns out that the standard error of the sample proportion for it turns out that the standard error for the sample proportion estimator, the p-hat estimator, it has a nice formula. Here it is. The standard error for p-hat is the square root of the population proportion times 1 minus the population proportion, but divide all that by the sample size n. Okay? So that's what it really is in math theory. Problem is that if you're a statistician and you're taking a sample only, you're not going to know p, So you're not going to be actually able to use this formula. But you can make a guess. You won't know p, but you're going to know p-hat, that sample proportion. And we do hope, and we've seen while playing around with the app, that the sample proportion at least does tend to be, kind of approximately p. So why not replace the p with p-hat in the formula here, and that way you'll have an approximation to the standard error for p-hat. Square root of p-hat times 1 minus p-hat over n is the standard error. That's what we'll do in real life when working with actual data. So let's try an example out. Let's switch data sets and think about M111 survey, because that data is a sample from a population. It's 71 people sampled out of the population of all Georgetown College students. And I'm going to pretend now that it's just like a random sample. And why don't we figure out the proportion of people in the sample who are female, okay? There's a nice little R function called prop. And if you tell it the variable you're interested in working with and the data set that it lives in, as long as that variable has just 2 values, and sex does, it's male or female, then it'll look at alphabetically the first value, which is female, and it'll tell you the proportion in that data that's female. And so you get out 0.563. I think we should just do this in RStudio, make sure this is really working. Copy, paste, and yeah, 0.563. So 56.3% of the sample was females. And actually, just because I remember, and I'll remind you, there were 71 people in the sample, and 40 of them were females. And if I just do 40 divided by 71, I get the 0.563. So prop is not doing anything super sophisticated there. It was just tallying up the females and dividing by how many people were in the sample. Just a simple old sample proportion. Okay. Now, that's the p-hat, but what's the standard error? Well, mathematically, it would be the p-hat, 0.563, times 1 minus 0.563, divide by 71, take the square root. And if you did that on a calculator, you'd get about 0.059, which is roughly a 0.06, 6%. So remember, the general template for interpreting standard errors in the context of estimation is you say that the parameter is about equal to the point estimate, give or take a standard error or so. And so if you're working with proportions, the template would be the population proportion P is about equal to your P hat, give or take a standard error or so. So in this particular example, you can say the percentage of all Georgetown College students who are female, that's your P, is about 56.3%, that's your P hat. Give or take 6%, that's your standard error, or so. So knowing the P hat and the standard error for P hat gives you a decent idea about where the real population proportion that you wish you knew, where it might be. So just like you can get the population, just like you can get the sample proportion with prop, you can also get the standard error for P hat using R. But you need to know the sample proportion, and you also need to know the N. If you're ever in doubt about like the sample size when you're working with a data set, just ask for how many rows there are in the data set. That would be your sample size. And you come out with 71. That'll work for you as long as everybody in the data actually answered the question. So then you could use R like a calculator and say squirt the 0.563 times 1 minus it divided by the 71, and you would get this result. So you'll have some times when you need to compute a standard error for a P hat for yourself, and all you do is you just do this kind of calculation in an R code chunk. Now, I'd like to circle back to the notion of unusual data values, which we analyzed in terms of z-scores. You can do something similar when you're thinking about what a parameter is versus what you might have thought it might be based on your data. So let's talk about surprise. So remember z-scores. We would be surprised to learn that an individual had a z-score of more than 2 or less than -2. Because a z-score was how many standard deviations the individual was away from the mean of the group. You can do the same kind of thing in terms of parameters. As a rule, you're going to be surprised to learn that the parameter is more than 2 standard errors away from the point estimate. Now, you're not going to learn these kind of things usually because you don't know the parameter. But the idea is that, like, if you took a sample and you got your point estimate and you got your standard error, and then like God came down and just sort of told you, hey, the parameter is actually blah, this value. And you computed how many standard errors the parameter was away from the point estimate, then if it's more than 2 standard errors away, it's just like z-scores. You would be surprised to learn that. You'd be like, wow, we must have gotten a really weird, unusual sample to be so far off. So that's the criterion we're going to adopt. Let's see what this would be like. So like in the case of the Math 111 survey data, would it be surprising if God came down and told you that, hey, actually, P is 60%. P is 0.6. 60% of all Georgetown College students are female. Would you be surprised? Well, check it out with the z-score. Take the P hat that you actually got in your data, see how far away it is from the real P, and divide by the standard error for P hat that you computed. So 0.563 minus 0.6 divided by 0.09. Now that's about a minus 0.63. And so your sample proportion was a little less than a standard error below the parameter that it was trying to estimate. Well, that's not too surprising. things are typically within a standard error of what they're trying to estimate. Not surprising at all. That can happen easily by chance variation. On the other hand, suppose God came down and said, hey, actually, 70% of all Georgetown College students are female. Would you be surprised? Well, let's see. 0.563 minus what I've just been told the population parameter is, divided by my standard error, is a negative 2.32. Wow, my sample proportion was more than 2 standard errors below what the population proportion is, at least as I've been told it. So that must mean, if God's right about what P is, then that must mean I got a really kind of unusual, unlucky sample, as it were. One with like a unusually large number of males and unusually small number of females in it, to get such a low P hat. Who knows if the z-score were like big enough, I might even start like arguing with God, like, are you sure? Didn't you make a mistake or something? So I would like you to kind of think about using z-scores like that, because that's going to become a big theme as we move through the rest of this course. The z-score for an estimator is the estimator minus the parameter it's trying to estimate divided by its standard error. And it can tell you how surprising it would be to learn that the parameter is that thing. Okay, next time we get together, we'll address that feature we saw in the app where the density plot of the p hats was shaping up to look kind of bell-shaped when the sample size was larger. This has to do with the central limit theorem, and wait for it in the next screencast.